Hello friends, in this video I will explain how to solve the problems on one-dimensional bar elements. The problem statement is like this. Using the direct stiffness method, determine the nodal displacements, stress, reaction forces for the figure as shown. Here the figure is shown like this. It is stepped bar. At the extreme left end it is fixed. At the extreme right end there is one force is acting. That force value is 5 kilonewton. One more force is acting at the change in cross sectional area, at the place where the cross sectional area is changing. That value F is 10 kilonewton. Both are opposite in direction. Here we have to make some assumptions which direction is positive. In this problem I will take towards right side is positive direction, towards left side is negative direction. That's why I have written here the force which is acting at the cross sectional area which is acting towards left side, that is negative 10 into 10 to the power of 3. One more force at the extreme right end that is acting towards right side, that I will consider it as positive. That value is 5 into 10 to the power of 3 Newton. That is positive. This assuming direction is left to us. Cross sectional area of each element is given, that is A1 and A2. Young's modulus of both the elements is given, E1, E2, and forces that are acting, that is also given. Now first step of the problem, that is FEA model, that is line diagram of the bar element I have drawn, and I have given node numbering also 1, 2, 3 like this. Started from extreme left end and ended at the extreme right end. You can go in reverse method also, but I have started from extreme left end. And cross sectional area change, that I will take it as node number 2, and extreme right side I will take it as node number 3. And Q1, Q2, Q3 are the displacements at node 1, 2, 3 respectively, and F1, F2, F3 are the forces that are acting at node 1, 2, 3 respectively. Next, length of the elements are also given clearly in the diagram, that is 50 millimeters. That is same for both elements. Now elemental stiffness matrix. The equation is like this: K equal to A E upon L, 1 minus 1 minus 1 1. Here suffix 1 I have written for all the notations, that is A1, E1, L1, because it is for element number 1. Now substitute the values: A1 150 millimeter square, E1 2 into 10 to the power of 5 Newton per millimeter square, L1 is 50 millimeter, where K is the stiffness matrix. Now calculate this part: A1, E1, L1, that comes as 6 into 10 to the power of 5. Here it is. Actually 6 I have multiplied inside, and 10 to the power of 5 I have kept outside only. And column numbers and row numbers are written there, that is 1 and 2. Why particularly 1 and 2 only? Because in the diagram we can see that for element number 1 nodes are 1 and 2. That's why for K1 it is row numbers and column numbers are 1 and 2. And 10 to the power of 5 I have taken outside. For the next stiffness matrix also the same value you have to take it outside. Then only it is possible to add both the stiffness matrices. Now how much value you are taking outside, that is all left to you. That is up to you. I have taken 10 to the power of 5, so remaining value only 6 I have multiplied inside. So K1 becomes 10 to the power of 5, 6 minus 6 minus 6, 6. Similarly, find out K2. Substitute the value of A2, E2, L2 Now calculate that value of E2 upon L2, that comes as 1.4 into 10 to the power of 5. So again, as I told, same value we have to take it outside the matrix. That's why 10 to the power of 5 I have taken outside. Remaining value is 1.4, that I have multiplied inside now. So K2 is 10 to the power of 5, 1.4 minus 1.4 minus 1.4, 1.4. Here I have written row and column numbers are as 2 and 3, because for element number 2 the nodes numbers are 2 and 3. Now next step is finding the global stiffness matrix. Global stiffness matrix is nothing but stiffness matrix for entire element. So this we will get by adding K1 and K2. So K equal to K1 plus K2. How to add these two? See here, this is one of the important step. What I will do, first I will write the matrix and I will write outside as 10 to the power of 5, because it is common term. After adding also, this remains as it is outside, and inside the size of the matrix remains as 3 cross 3, because total nodes for this element are 3. So size of the global stiffness matrix 3 by 3. Initially I will write this matrix as blank, and I will write column numbers and row numbers. Column number says 1, 2, 3, row number says 1, 2, 3. Here I have written already inside element also. How those inside elements comes in this global stiffness matrix? There is a method you have to follow like this. First write a blank matrix. In the place of column 1 and row 1, I have written as 6. That you will come to know how it comes. Looking at K1. See, at K1, at column 1, row 1, the value is 6. That's why in global stiffness matrix I have written as 6. Similarly, here at column number 2 and row 1, I have written as minus 6. You can check that. In stiffness matrix 1, column 2, row 1, the value is minus 6. That's why in global stiffness matrix I have written as minus 6. Similarly, at column 3 and row 1, I have written as 0. You can check both the stiffness matrix. Column 3, row 1, there is no value. So I have written as 0. Similarly, write on all the values, but especially in the place column 2, row 2, I have written as 7.4. That value is 7.4. How it comes? Say, that is very important. When you come to the stiffness matrix 1, K1, in the place of column 2, row 2, the value is 6. The same place, that is column 2, row 2, is available in stiffness matrix 2 also. Check here, column 2, row 2, here the value is 1.4. So at the place of column 2, row 2, two values are coming. One is 6, another is 1.4. Both the values we have to add. After adding, we are getting as 7.4. See here in the global stiffness matrix, in the place of column 2, row 2, we are getting as 7.4. Similarly, write down all the values of the matrix by applying same procedure. Next, step number 3, that is nodal displacement vector Q equal to Q1, Q2, Q3. These values we are going to find. Step number 4, nodal force vector F equal to F1, F2, F3. F1 I have written as 0, because there is no force acting at node 1. F2 minus 10 into 10 to the power of 3. This is the force acting at node 2. Here in the diagram, see here, at node 2 means where the cross section area is changing. At that place there is one force is acting, that value we have taken as 10 kilonewton. But I have taken sign as negative because assumed positive direction is towards right side. This is opposite to that, that's why sign is negative. Come back. And F3, the force acting at node 3, that is 5 into 10 to the power of 3, which is acting right side. That's why we have taken it as positive value. Next step is equilibrium equation. That is step number 5. That equation is like this: KQ equal to F. K means global stiffness matrix, Q global load vector, Q is displacement vector, F is load vector. Write on all, we will get this equation. matrix equation. Next step is step number 6, that is applying boundary conditions or imposing boundary conditions. It is nothing but eliminating particular row and columns. That is, if you are solving by elimination approach, we have to eliminate particular row and columns. Which row and column I have to eliminate? That we will come to know by looking at the diagram. Or one more thing we should know, that very important is wherever the displacement is known for us, or at which node we know the displacement, that particular row and columns we have to eliminate. In this diagram, here in the diagram, it is very clear that at extreme left side, that is at node 1, it is fixed. It means displacement at that place, at node 1, displacement will be 0. Hence, displacement at node 1 is known for us. Hence, we have to eliminate row 1 and column 1. I have eliminated. I have drawn a line on row 1 and column 1. After eliminating, write down only remaining values. Here I have written remaining values here like this. So calculate this one or solve these two equations. Write this matrix in the form of equations now and solve them. We will get the values for Q2 and Q3. Q1, as we already know, that it is 0. So Q2 is minus 8.33 into 10 to the power of minus 3 millimeters. Q3 0.02738 millimeters. Next, finding the stresses. For finding stresses, the equation is like this: sigma equal to E upon L minus 1 Q1 Q2. So for element number 1, that is sigma 1 E1 upon L1 minus 1 Q1 Q2. Q1 Q2. Why Q1 Q2? Because for element number 1, the nodes are 1 and 2. Here we will come to know. See here, for element number 1, E1, element number 1, it is nodes are 1 and 2. That's why we have taken as Q1 Q2 in this equation. Substitute value E1 and L1 and simplify this one. We are getting the sigma 1 as minus 33.32 megapascal, this value. Similarly, finding the stress for element number 2, sigma 2 E2 upon L2 minus 1 Q2 Q3. Here the values are Q2 Q3 because for element number 2, the nodes are 2 and 3. Here we will come to know. So calculate this part, and sigma 2 we are getting as 50 megapascal. The last part of the problem is finding the reaction forces. R equal to KQ minus F, where R is reaction. So K stiffness matrix, Q displacement, what we have already found in the previous step, minus F, that is load vector. First K and Q I will multiply. I will get one matrix. I will write there. Then I will subtract that matrix with force vector, force matrix. After subtracting, we are getting R1, R2, R3 as like this. R1 as 4998 Newton, almost it is 5000. R2 and R3 0. We will get the reaction force only if there is a support. Wherever there is no support, the reaction force will be very, very less, or it is 0. So in this way, we have to solve the problems on one-dimensional bar elements. Thank you.